Anyway, hi, I'm Joe, and this is probing pins for protocol polyglots. So you might have some questions about what all those words mean, or you may not. Who's heard of a polyglot before? So it's typically used in computers for like file types. So a file that is a zip file, but is also a PDF file, that is also a NES ROM, that is also an image file, that is also a zip file containing itself. That's a polyglot. Basically, you mess with the file protocol to basically follow two sets of rules at once. But those are files. These are protocols. So me, I'm Joe. I do hardware hacking stuff. And this is a presentation I gave at SuperCon back in November. Who's heard of the Badge Life add-on standard pinout? So the standard add-on, the silly add-on, the stupid add-on, or the shitty add-on, depending on where it's documented. Basically, it's 4 pins, right? 0.1-inch headers, and it's SDA, SCL, which is I2C signals, power, and ground. But of course, like this is a very loose spec. This is literally the spec. This image, I think it was a tweet. This is the whole spec. And so I decided to go for malicious compliance. So that year I made the micro badge, and you'll see the micro badge all the way up here is very tiny, right? I took advantage of a few things. You'll notice it's a very small badge. It has just enough room for basically the shitty add-on connector. And that's because the spec didn't actually say which way the voltage was supposed to go, whether it was supposed to be supplied by the badge or supposed to be supplied to the badge. And I made some extenders and some other things, and I had a little vest that, whoops, let me change the color so you can see. Little vest so you could I could hand out big bits and pieces of this micro badge and put something together. But it's tiny, right? Basically, it's an AT-Tiny85 microcontroller, which is basically just enough to turn on and speak I2C if that's what you really want. But that's no fun. I2C is a pretty standard protocol. You have a start condition, which basically says, hey, it's time to start talking. The device on the other end is going to listen, and it's going to see a bunch of pulses on a clock line and check the data every time the clock goes low. I think, yeah, every time the clock goes low, it checks the data, right? And if it gets its address, it'll respond, and if it doesn't get its address, it doesn't respond. And then there's a stop condition, which says, hey, I'm done. Free up the lines for other people to use. I2C is nice because it's a multi-device interface, so multiple controllers can be on one pair of wires, and multiple devices can be on there as well, and they can take turns very nicely. But that's a lot of work, and that's in code, and then something on the other end needs to listen to I2C and respond to it. But I had a bunch of these WS2812 LEDs, the serial addressable LEDs, which have a very interesting protocol where basically you have ones and you have zeros, right? And the ones have very wide high periods, and the zeros have very narrow high periods, right? So it's a return to zero code. It starts out high, it stays high for a long time for a 1 and goes low, or it starts out high for a short time and then goes low for a long time for a 0. And so I'm like, okay, well, why don't I just spit this out on these wires? It says it's supposed to be I2C, but can I use the same wires for this? The other thing this protocol has is it has this reset state. And if you basically don't have enough toggles in a certain amount of time, it'll just reset. So outside of the start and stop conditions for I2C is undefined. Don't care. I don't care what happens. Anything can happen. So at that point, we can just flash LEDs using the WS2812 protocol on those wires and call it good. And that's what I did at that point in time, right? Start condition and stop condition, anything goes on either line by itself, right? The combination of both lines going and changing at the same time is what causes devices to start listening. So as long as we avoid that, as long as we stick to one line or the other, we can do whatever we want. Also, between the start and stop conditions, while SCL is high, anything goes on SDA. So if we have that I2C protocol, right, while it's high, this signal is supposed to change, right? So we can actually take advantage of that if we want to mess a little bit deeper. Now, for the WS2812 protocol, anything less than 28 bits is ignored, right? If it's not close to 400 or 800 kilohertz bit rate, it's also ignored. So it is unfortunate that 400 kilohertz is a common I2C speed. But for the most part, we can just be sure that we're not always going to have the right number of bits, the right number of times, the right number of transitions, and the right number of places. So let's just not worry about it. So basically, let's reuse the same wires for I2C and WH2812, and both devices work fine, which is great, don't you think? So this made me think about like where else can we find this forgotten bandwidth? And basically, what it comes down to what is undefined or versus defined in a protocol. What's user supplied, right? If it's user supplied, then it can be either a 1 or a 0, and we can like maybe do a packet in packet kind of thing. What is invalid? What can we do to basically poison a transmission to say, hey, everything I just said, ignore it, or everything I'm about to say, ignore it? So when we think about protocols, we think about packets, right? And whether it's a packet level, a higher level, or it's just like framing, a beginning and an end, a start and a stop bit, enable or disable, what makes it correct versus malformed, right? And then those malformed packets, what happens to them? Are they reinterpreted? Are they error corrected? Or are they just thrown out and ignored? So let's look at some protocols and see if they're polyglot friendly. We talked about I2C already, right? Again, before the start condition, after the stop condition, fair game, anything goes, right? As long as this signal is high, fair game, anything goes on this wire. But if we have any combinations, then we get into the area where the protocol might disagree with the things that we're trying to do, right? And yeah, that's basically what we just talked about before. WS2812, again, we have 1s, we have 0s. If we don't have something going at the right speed, it's ignored. If we have nothing happening for long enough, it just resets. If we don't have 24 bits, it's trash, so we ignore it. So think about all these don't care conditions, all these like doesn't matter or ignored or malformed. And that is all basically, on the one hand, it's a don't do this if you're talking to these devices. On the other hand, it's okay to do this if you want to talk to something else, right? So one device's instruction and data sheet is another device's like permission slip. Now let's look at UART. UART is a little bit more interesting. So we've got a start bit and a stop bit, right? And that start bit has to be low, and that stop bit has to be high, right? And now when that start bit happens, what typically happens, the device on the other end synchronizes to that, and we'll basically say, okay, well, we'll go a half a bit, and then we'll go a full bit, 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 right? And one more full bit. And it'll sample one time. So even though this signal might be going at 2400 bits per second, right? Which means this is 1/2400th of a second, it doesn't matter what's going except for when I'm sampling. So if I have a precise sampler, I can do whatever I want over here and over here as long as I'm doing the right thing there. Now here's the other thing, is this stop bit at the end is also important. This stop bit has to be a 1, right? If it's not a 1, it basically is called a framing error. It means that the transmission that I just had was wrong. I didn't time up my timing right. Something went bad. Like, just ignore this. Typically what happens is the hardware is going to see that happen and throw it out, ignore it. So can we take advantage of that? Let's see. So what the stop bit is 0. It's a framing error. So we can do a start bit followed by 8 bits of whatever the heck we want. Not even 8 bits, but 8-bit time periods, followed by a 0. And that 0 is going to be not a stop bit, which means it's going to be an invalid packet, which means the whole thing's going to get thrown out, right? So basically start bit, whatever you want, and a 0, and you've got permission to do whatever you want. Cool. Next, we've got SPI, Serial Peripheral Interface. And this has a lot more pins. So we've got a select signal, and that's what's going to start and end the transactions, right? And then we've got our clock, data in, and data out. Now, SPI is actually designed to let you use multiple devices on the same signal, so long as each one has its own select signal. So as long as we are not selecting anybody, we do whatever we want on those signals. But we also have another bonus. If we're using a clock, right, we can go inside this clock. As long as the clock stays high, right, we've already done our sampling of the data on the rising edge. We can do whatever we want until the clock rises again. So we have a little extra don't care space, but it's just a little bit harder to use. So every other pin is now a don't care when CS is high, even the peripheral out controller in, which is an input as opposed to an output. The spec actually tells devices that they should be high impedance, tri-state. They should not speak on that wire, even though it's their wire to speak on when it's their turn. So depending on the delay, only rising clock edges matter. There are different versions of SPI that use the falling edge for some things, but whatever. If you pause the clock, if you keep the clock paused for a long time, that's totally within spec. That's totally allowed by SPI and lets you do whatever you want on any of the other wires. How about USB? So we're getting up there. This is USB low speed or full speed. It gets more complicated with high speed. One of the things you've got with USB is you've got differential signaling. So you see that basically it's fake differential signaling, though, because it's USB. Everything in USB is fake. Is we have two signals, and one is opposite the other, except when it's not, right? Which is single-ended zeros. Single-ended is when you have a signal that goes up and down versus differential when you have a pair. So we say single-ended zeros, we both go to 0. That's our end of what's it called? End of packet or end of frame? I can never remember with USB. It's our end of packet. But we also have this other thing, this CRC right here, which means if we go and we say, OK, we've got USB wires. We did the sync packet that says we're going to start sending data. Now we do whatever the heck we want over here, send LEDs, light up things, send, secret codes. As long as we have an invalid CRC at the end, it's OK, because it's just going to get dropped and thrown out, right? So differential signal is not a big deal. Everyone has CRC. A bad CRC is a don't care. That single-ended zero reset can be a problem, because if we do that in the middle of our noise, we might accidentally reset the whole signal, and it might start parsing our data properly, which would be unfortunate.
Can I ask a quick?
Absolutely, yeah.
I'm just trying to understand what you're trying to do. You've got 4 pins, and you're trying to stream multiple protocols over those 4 pins simultaneously.
Yeah, this has no.
Using different timing.
Yeah.
And different, and as long as the timing and the alignment lines up on those protocols and they don't interfere, you can stream multiple protocols over those 4 pins.
Yeah, I want to use a single set of wires and have it be interpret as multiple protocols as valid data on different protocols at the same time. So yeah, so let's get fancy with this. So that's a nice clock you got there. What if I were to use your clock signal as a UART, right? Now, SPI says, hey, we're going to have a clock. Every time the clock goes high, something happens. Every time the clock goes low, something happens. That's great. But the clocks themselves are not necessarily required to be regular, right? It doesn't have to be a 4 megahertz clock or a 1 megahertz clock or a 2 megahertz clock. That 4 megahertz clock could actually be a valid UART signal, right? And you can use that to go and transmit some extra data while you're in the middle of doing your SPI thing. Now, SPI usually runs at a megahertz, and UART usually runs at kilohertz. So you're going to have some speed mismatch issues. But again, if you are trying to hide data, right, you might capture this with a logic analyzer. You would run your analyzer on it and say, oh, this is valid SPI. It's just really slow. But if you look at it carefully, if you look at the actual ones and zeros over time, you might say, hey, there's something going on with this spacing. This is not regular. This is another protocol we're embedding inside of it. So you could say, oh, OK, SPI, that's great. Now there's UART hiding inside my SPI, which is even better. But you could also look at the other way and say, like, well, my SPI is hiding inside my UART. Yeah? And the exploding mind is like, wow, those are actually both the same thing. So what if your UARTs had their own UARTs, right? So if you've got about 1.5x your baud rate between the start bit and your first data bit, right? So don't let that extra data space go to waste. So here's UART, right? And UART's going to be in idle state until it has a start bit, right? The start bit is what's going to start the timer. We're going to do our sampling, checking our bits, and our stop bit, right? Now, what happens if the stop bit is low? It's garbage, throws it out. But we'll say for now that we want to transmit some good data. Now, this is also UART. So here we go. We have our start bit, right? And we have some space. And then we have our stop bit. But our stop bit is low. So we get our framing error, right? And then our stop bit is low again. We get a framing error, right? So what we can see here is we interpreted this. And what did we get? We got our C, our letter C. And then we got nothing, because all those packets were just dumped. They were garbage. Now, what if we, at the same time, just had another protocol? So this protocol analyzer is going at the baud rate for this size bits, whereas this protocol analyzer is going for much bigger bits. And we can see that here we've got our C, and we've got a bunch of, again, an at. We've got an at. Actually, that's also a framing error, sorry. So all these framing errors don't actually mean anything. So on this UART, the actual output is just going to be a C. Whereas on this UART protocol analyzer, the output is going to be D. Make sense? So if you hook up a UART hardware device, like a Tigert or a FTDI board or something, and you set it to this baud rate and you listen to it, you're going to get different outputs depending on what speed you listen to it on. If you hook up a logic analyzer and you capture it, you're going to get different outputs depending on what you set your protocol analyzer to look at. Yeah.
How typical are these loose sets of protocol rules? Like, it seems as though if you can go faster, you can put stuff in there. If you don't piss this protocol off by doing some little, are all protocols like this protocol where you can apply this kind of generically?
So a lot of the low-speed serial protocols are very much like this. Once you get into a parallel protocol like a NAND flash protocol or a DDR RAM protocol or something like that, that gets a lot more complicated. They still have their don't care regions, their beginning and their end, but you can go outside of those. But the protocol, when it's actually in process, is a lot more precise and timing precise when it gets to those faster protocols. But again, it all depends on the protocol. The protocol has rules that tell you what's valid and what's not. So just pick out what's not valid, and that's it.
Like the specifics.
Yeah.
Please go on.
Just do what they tell you not to do, and you're fine. Yeah.
In the smaller like in the smaller there's like shorter wave. There are small spikes that couldn't they like create a risk of starting with a 1 bit which were not let start and then starting later and offsetting time.
Let's go to the code. So basically, what about those little spikes? Are they going to cause problems? So if we want to write a bit, right? Basically, we have a value and a length. So we're gonna write our bit, and then we're gonna delay for a certain amount of time. Make sense? It's how we write bits. Now, if we want to do a byte, right, we can just write a bit over and over again, and we have a start bit, we have a loop that's going to do 8 bits, and then we have a stop. Now, I also want to be able to transmit other stuff, right? So I have this bad byte function, right? And what this is going to do is it's going to do a start bit. It's going to do its 8 bits, and then it's going to do a bad stop bit, right? Which is going to say it's a framing error, so like you're garbage, don't do it. And then it's going to go and set to the proper value, right? So for the duration of the stop bit, it'll be the wrong value, which means this bad byte is going to write a byte, but none of those bits actually matter.
Is this bad byte typical among protocols? It seems slightly different in terms of how it's reacting. Like a protocol has a built-in ignore what we just said, and that gives you a free.
Yeah. So this is just UART. This is my implementation specifically for UART, taking advantage of using that stop bit. Yeah. So now I have my these bytes that I'm writing. I want to call each of those bytes a bit for my upper high level protocol, right? The higher level is running, a tenth the speed because I have to write 10 bits, 8 bits, a start bit, and a stop bit for every 1 bit of this protocol. So if I want to do a hidden byte, right, I'll write a byte, and then I'll just put like the remainder of the time the value I want to actually read, right? And if I want to do a bad byte, but the remainder of a slow byte, right, basically I do the same thing with a bad byte. Am I making any sense yet? So I need to constantly be spitting out a stream of bits and bytes, right? And so I want to write bytes that I want to actually read, and I want to write bad bytes that disappear, right? And that's what we put together so that I'm building up the layers here. So we want to write our hidden bytes, write a hidden byte, and then we write 8 hidden bytes for each of the 8 bits of that byte, and then the stop bit, and then we loop that. So let's go back to the diagram that we can see that actually happening, so it'll make a little more sense. So here, right, we have C, and we want to write a start bit, and we want to have 8 data bits, and then a stop bit, right? Now we need to do a bunch of other stuff, right? But we always want to make sure that we have a start bit followed by something followed by a stop bit that's incorrect. Start bit, something, stop bit that's incorrect. Start bit, something, stop bit that's incorrect. Okay? Now, at this higher level, right, basically every time I write a bit here, I'm actually writing a byte up here. Does that make sense? So every time I want to write a 0, I have to write a byte up here, and this actually just goes and sees that pulse and calls at the beginning of a new byte, even though it's just a glitch in the middle. We have this next bit right here that we're writing, and it gets a 0 because it's still staying 0 from before. Right? At some point, we have this glitch. So the fast protocol thinks there's another bit going there, but it then ignores it because it's got the wrong thing. But this thing still gets the 0 it expects. We do have this 1 that we want to have to happen, right? And in order to get that 1, we need to make sure that that high value is there at the right point in time, which means we've got an idle thing happening in this bit. Yeah?
Is the right way to understand the slow stream is that it has a very accurate reading, so it's not going to pick up what you've written, right? It will just get the absolute Laplacian of the instant it reads, but it reads very slowly, so there's just a huge empty gap for you.
Yeah, let me kind of clarify that. So if we erase all these markups that I added, right? If we look, basically, most of the time, it's getting 0s. Even if it's got that little spike, that's typically not enough. But every time we've got a 1, we've got that big, wide 1 that we're reading. And then a stop it, we've got a big, wide 1, right? So basically, I'm spitting out the 1 when I know I need to spit out the 1. And then the rest of the time, I'm spitting out the right noise to make it so that the fast UART ignores it. Yeah?
Just to be clear, so like the way it's working is that the start bit is at the falling edge. So as long as you're holding that high, the fast protocol doesn't start at you.
Yep. Yeah. Yeah. But in order to do a low, I need to do a stop bit at the right spot in time. Yeah.
So, but the reason the gaps is the fast protocol exists.
Yeah.
Because it's the start bit is the falling edge. Right.
Yeah. And all of this, like, I'm giving a somewhat serious presentation on this, but this is all kind of ridiculous. This is just stupid tricks, okay? So this is like, okay, if you have to cram another I/O into a system, you don't have any extra pins for it, or you need to like, cram an extra controller or device microcontroller or something. Basically, you can use protocols in ways they weren't really intended. It's totally within spec. It just is a little bit sketchy, right? Actually, it's a lot sketchy. So protocols can a whole lot more than you might expect. You have to understand that like following the rules is about knowing the rules, right? But it also is knowing when you don't have to follow the rules, right? So that's kind of what it is with UART. With UART, you have to do the right things at the right time. And if you don't do those, those are consequences. And if you take those consequences in mind and calculate that, oh, consequences are not a problem, I actually wanted to ignore this data, then you've got an opportunity to go and cram more data onto those wires. So do this at home, do it for fun. Don't do this at work. This is not professional level coding. This is not. This is like, I mean, if you want to do it, go for it. But I won't tell you what to do. But sound like fun? Make sense? Any questions?
Yes.
Yes.
So,
No, I don't do consulting on this.
Okay, so
Yeah.
basically whether or not you do, if I wanted to cram 2 devices onto the same line somehow to make my life easier, is this ever going to make my life easier? Not for messing with an external device, but actually I control the devices and I would like to put them both down the same height. Is that a viable thing, or is this more
So the better. When would this actually make things easier instead of making them more complicated? Perhaps.
So say I have an acoustic sensor and an electrical emitter receiver. And so the acoustic sensor is probably going to operate the acoustic range.
Yeah.
And then you've got the same kind of frequency situation, electrical signal. There's some protocol that I combine the two upstream signals somewhere, I guess.
Well, so something I'm thinking of right now is if you had like a temperature sensor that was an analog temperature sensor, right? And that basically had a voltage, and that voltage correlated to a whatever. And you could just use that as like a temperature sensor, but you could also use that as the pull-up on something like I2C. And so like your I squared C, like your 0 would be 0 and your 1 would be the voltage that corresponds to your temperature, right? So like,
Whoa.
yeah, like,
In my mind,
so yeah, basically like, you know, okay, if you're pin constrained, if you're space constrained, like what else can you plug on there? And what are the consequences of wiring things up stupidly like this?
Likely on a circuit that breaks one protocol when it gets too cold out and causes the
Yeah, yeah.
So you've got an implementation running where you've got two UARTs on the same line.
Sorry, what?
You have an implementation running where you've got two.
Yeah. I mean, that was a capture of it. So that's a capture of a protocol. Oh no, that's SPI. Sorry. This one. That's a capture of some Arduino code that was on the next few slides.
So I'm thinking you could actually have like a debug board running at high speed and you're actually rolling problems running at low speed thing, you're just doing an RS-485 or something like that with just a transceiver on it and you've got two on one thing. Standard error, standard out. Still standard error, standard.
Yeah.
security implications.
Security. How about exfiltrating data? Yeah. So, you know, I don't know. Exfiltrating data is kind of fun. You have all these sensors all over the place that are doing all sorts of sketchy things. And you think they do what they say they do. And then suddenly it turns out they're also recording audio and exfiltrating it somehow. That'd be cool. I don't know.
So you go cooler than that?
Yeah, sure.
Come on.
Oh, you want me to go cooler than that? I thought you had an idea.
I do, but like it's your talk.
Okay. I'm done. I'm done with my slides. There we go. We're at questions. So,
Okay.
yeah, hold on. Yeah.
Similar with comment and or an addition, but you can also do something similar with file formats. The game, use it as intended to get a game. For example, the ELF file format used in Linux. So Linux doesn't actually read the whole header, so you can just write like the code inside the header and make it an extremely tiny ELF executable, even though it's not really supposed to be that, because like Linux doesn't actually read the whole header, so you can create like a super tiny.
Yeah, the inspiration was that like, oh, we've got all these file formats that can be polyglots, right? So can we do the same thing with like hardware protocol? So yeah.
Are there new devices that might be enhanced by having this additional bandwidth on their line?
Yes. Oh, I don't know which ones. So the original example was this AT Tiny 85 itty bitty thing, 8-pin microprocessor. And of course now like my go-to microcontroller costs a fraction of the cost of this thing, and it has 4 times as many pins. So like the requirement isn't the same as it used to be. But yeah, you're always constrained by pins and traces and space. And you know, if you're dealing with a device that's already implemented and you just want to rewrite the firmware and add a capability to it, but you don't have space for a UART or a additional I2C device or something like that.
Well, because you've got now on things like the CH32 you can get an 8-pin something like that. But it's got way more memory than an X.
Yeah. Well, but I use the DFN QFN 20 because it's smaller and cheaper. Yeah. Smaller and cheaper and more pins. Yeah.
I was thinking, does UART have like I'm not sure about the programming for UART, but if somebody has like an error correction detection, like, oh, this frame's corrupt, like ask for that frame again, like TCP packets?
I think most interpretation or most implementation of using UART basically ignores everything that's a framing error. So if you did do that, which I don't actually know off the top of my head what libraries would do that, like, you know, PyFTDI, I don't know if it gives you access to the error count or anything like that. That would be
mitigation for this data exfiltration.
Yeah.
Late last year, I've been running some ESP32s, Home Assistant, DME 280s, and with I2C, and then for months and it worked great. And then suddenly I2C stopped working and I can't, any old device, new device, the I2C detect or scanner detects no devices. Is there somewhere I can, jumpstart I2C again?
So my guess, my experience with stuff like that is like I squared C, something happened with your pull up. It's not connected properly, or it's pulling up too strongly, or it's not pulling up at all. And so my approach there is like hook up a logic analyzer and see if anything's happening, see if the device is talking, see if there's a response that's coming back, and then figure out like what's going on. But yeah.
If we can help with that, we don't. Article and Larson.
Oh, great.
So these P32s get a little squirrely with it sometimes.
I don't, yeah.
Oh, yeah, for sure.
Well, the other thing is if you've got like 2 week a pull up and it's constantly pulling the pins up, then it overdrives and it burns out your driver, like that kind of stuff could be a problem. I don't know. Yeah. Any other questions? Who's gonna go home and do this? Who's gonna go to work and do this? Who learned something useless? Okay, there we go. That was my objective. Make sure everybody learns something useless tonight. So cool. Thank you very much.
Thank you. Great talk.
Let's